Afternoon, everybody. We're done with the DC generator and we'll start induction machine, and I believe it will take with us like 2 weeks. And before I start induction machine, I just like to tell you that I'm very happy about your progress in the course. I mean, most of you are doing really well, much better than before in the lab and in the exam, when I look at the exam, So if you continue like that, I promise you that the final is going to be very simple, the easiest one. Be nothing in it, just to take you like a few hours to review. That's a promise from me, because I mean, you are really very happy about your performance right now, especially in the lab also.
I got a question for you.
Yes.
Come the final, like I know it's like a month off.
No problem. No, it's soup.
Come the final, can you like open up the tests to where we can look back at them and like review the question?
We can bounce back again. Well, let's see. Maybe I don't know. Maybe I'll do it in class. But if I do it online, I can do it to bounce back, to that question.
That's fine.
Just it's like a recommendation from the university if I have online tests.
He said you have the solution posted, so that's fine.
Oh, are you talking about the final or the exam too?
Oh, like for the past exam.
Oh, yeah. I will overprove. Yes.
Okay.
Yeah, no problem. I thought you were talking about the final. Okay. All right. So induction machine, I cannot say it's one of the most important machine. It's the most important machine that's used in industry, in many applications, even in our households. It's rigid. It doesn't need maintenance a lot. It's really a horsepower of all machines as a motor, not as a generator. Yes, we use it sometimes as a generator, but it's famous to be a motor, to drive appliance. Maybe there is exceptional in renewable energy. Sometimes in renewable energy, they start to adapt to work as a generator for some reason. But in general, it's the best motor. Most likely used in industry, and as I said, used as a motor. There are different types: single phase, 2-phase, and 3-phase. Usually, single phase, it's used in some application like appliance in the house. Like if you look at the washing machine, you'll find here the motor. That's induction hidden there. The lawnmower, the mixer, the juicer, all induction. Single phase. Turntable, refrigerator, also you find in the back, there is an induction machine, there is a motor that operating the compressor. So, I mean, all the appliances, almost all the appliances that needs something to drive it, to rotate it, to move it, it's induction machine, but it's single phase. And then you got in industry, you got the big one, the 3-phase. So they're used as pumps, fans, compressors, paper mills, textile, the whole industry. Most of the industry around the world use induction machine as the driver for their machines and equipment. And there is, one application. I work one time with that for because I like control. It can be used. There is 2-phase. Motor has 2-phase, and it can be used in servo application. What does it mean, servo application? Like, if I want to control the direction of something far or connected by wire, I can have something steer it like that. It will rotate the same angle. So you can make control, position control, speed control. We call it servo application. That's the 2-phase. That's most of the application. Well, if you go for the construction or the parts in the in induction electric machine, it's like almost most of the machine, but there is different. For example, in DC motor, you have the stator and the rotor. You have here a stator and the rotor, but the stator in DC machine, you have like 2 poles, 3 poles, winding. You can have permanent magnet. This one does not have permanent magnet. The machines that have permanent magnet, DC machine, synchronous machine can have also stepper, you can have, but induction machine does not have permanent magnet. It has winding in the stator that it create the magnetic field. And today We are going to talk about how they create the magnetic field in the stator or in AC machines in general. And then you have the rotor, and I'm going to explain in detail each one, but I mean, this is the general, you have stator, you have rotor, you have cooling fan, you go in this direction, you have cooling fan here, especially if it's three-phase motor, it needs ventilation. And also, you got here the box. If you see the box here, that's the terminal box. The stator, that's three-phase, by the way. So this box, you have like 4 wires, and you got the option to connect it as delta or as a star. I dealt with even 3-phase. I have in my farm like 3-phase induction machine, and sometimes I connect delta and start from the top. You can fix it. It's really handy, very handy. Because I mean, we use it as bump. I mean, if you have well, if you want to get water to water your farm, then this is the best one to use. So this box gives you the chance to adjust the terminal. It's very simple. It's like, I mean, you short something like that. I will show you now. We do it like that, make star, make it delta, very easy, very simple. And that's the shaft key that you have here, the shaft key, and the motor shaft, the bearing, the all mechanical. Let's see, I mean, the structure. That's the stator, fixed. And you see the winding here, they are huge induction machine. One time I was in a cement factory, and there was a problem in this machine. I was walking inside this room, walking inside the stator. Just imagine the size. This room was bigger than this room, like 3 times. And I was looking inside this morning, the stator, just looking at the winding. It was been, I mean, it's huge. I mean, when the factory, this only, they have many induction machines for cement factory, and there is one just didn't work for some problem in power system, something called harmonics. So shut it off. I mean, they were losing like million every day for one motor only. You have many. So that's the stator, and then winding in this, they put slots, and usually the stator is made outside cast steel to make it strong. And then you have the slots here, and you have the winding of the stator, and it can do it. You see, that's what I'm talking about. You can make a star connection, you can make a delta connection. So you have here the 6 terminals. So it depends how, if you connect it like that, horizontal, you connect this W2, U2, then you got the star. If you connect it in vertical like that, you got it's just simple, like very simple like that. So they are available for you to do whatever you want to do. Maybe you're asked why they changed from delta to star or star to delta. No, it's really important, because as you know that if you have the line voltage coming here, let's say that you have 208 voltage between line and line. So if you connect the delta, the same voltage you are taking, it's the same across the phase. If you make it star, so you're taking this value divided by radical 3. So you get to 120. So you have the option, you can get the voltage 208 or 208 or 120, 110 without transformer. So you can control it if you want to lower the speed, increase the speed, you want to have high starting, small voltage starting, so you are free to choose, you know, the application. So that's good. And we're going to talk a lot about this, because I mean, the magnetic field is produced by the winding in the stator. And it's really important. Why? Because when you look at the DC motor, you have the magnetic field, and the rotor has current from the battery, if you remember. So the current in the rotor and the armature produce magnetic field, and the magnetic field comes from the stator, interact with the other magnetic field in the rotor and the armature, so they produce the motion. They produce the rotation of the shaft. But here you do not supply current to the rotor. So how can you get rotation if you don't have current in the rotor and you have only magnetic field? Because to have, according to the rule that you know, to get something to move, you have to have 3 things, right? You have to have magnetic field, and you have to have electric current. Then you get the. So now you have magnetic field, but you don't have current. So how you get it? That's why they call it induction. You have to make magnetic field different than the DC. The DC magnetic field is constant with time. It doesn't change with time. Like, I mean, it's always direct like that, fixed, because it's produced by DC or permanent. But they do something here very smart. They produce rotating magnetic field from the stator, changing with time. So when the field changing with time and interact with the rotor, so the rotor produce the EMF because it's changing. If it was not changing, it was DC, nothing, right? Because you said that to produce any EMF, you got to have rate of change of flux. So that's the trick they did. Okay, we're going to do magnetic field, but not fixed like DC. We're going to make it produced by AC, and the current will be changing with time. And then, as a result, the magnetic field produced by the stator will be changing with time. So when it hit the rotor, it will produce EMF, but you will not have current in the rotor if it's open circuit. That's why when you look for the rotor has two types. There is one here, you call it squirrel cage. Squirrel cage, the squirrel cage, they have bars, as you see, and these bars replacing the wire. They are conductor. Of course, you see there are some slots there, they make insulation between them, but these, I mean, bars, they represent the conductor, no winding. And then when the magnetic field hit the rotor, will EMF produce, but they need current, because we know something to rotate, you got to have magnetic field and electric current. And to get electric current, this circuit has to be closed, short circuit. So they do, you know, there's a ring here that they connect the bars in a way that they are closing, making short circuit on them. Why they are doing that? So current can pass in these bars. And once you have current in these bars, then you have interaction between magnetic field and current. There is another type, they have wind. They want the rotor with wire, but they have slip rings. 3 slip rings. Why? Because they want to connect the wire to the slip rings to short circuit. Then you say, why 3? Simply because you have 3-phase rotor. You have 3-phase rotor, and if you look at the winding of the rotor like that, so if magnetic field hit, you have EMF here. You have E1, you have E2, you have E3 between the, but no current. So what do you do? Short circuit by the slip rings. So you have 3 slip rings short circuiting the rotor, one or the bars. So you have current, and once the current starts to be in the rotor, so you have interaction between the electric current in the rotor and the magnetic field in the stator. But this current is not produced by an external source. It's produced by the induction, induced by the rotating magnetic field from the stator. That's what they call induction machine. Because the current in the rotor is produced by induction. The EMF induced in the rotor winding because of the rotating magnetic field. Of course, I mean, the two, usually the small size of motor, they use the squirrel cage, and the big size of induction machine, they use the 1/4 type for ITS.
So there's a wire between the 3 slip rings?
No, the terminals of that, you see, I mean, the one rotor here, I have another, yeah, that's a good picture. This is the rotor winding. So you got 3 wires. So they get the 3 wires, they connect it to slip rings. The slip rings, you know why? Because when it rotates, the slip rings rotating with them, so there's no mass in the wire. But the 3 slip rings here, if you forget about the resistance now, they get wires from here and they short circuit. So you can see now it's just closed. If you go in a circuit, it's just closed everywhere. Short circuits, like, I mean, you short circuit these things through slip rings.
Right.
With the slip rings on the shaft, rotating in the shaft. That's number one. So like in the DC motor, you have commutator. So you are connecting the winding with the conductor, rotating with it, so it will not be messed. So you have connection between the winding and the shaft through separate 3 slip rings. Then these 3 slip rings, they connected by wires to short circuit. Yeah. But of course, I mean, to make it sense, it's handy. They don't short circuit completely, or you can say they short circuit through resistance, through restart. You see here? Let me just. They are connected to restart before they short circuit here. Why? Because you want to control the current. Said, okay, we're going to connect restart by a resistor. And you can change. The 3, of course, they are changed at the same time. It's like one slider. When you slide it, it changes the whole 3 resistance here, connecting as start. So when doing that, you can change the current because you can increase or decrease the resistance added to the resistance of the winding of the rotor. So in this case, in this way, you can control the current in the rotor. And when you control the current in the rotor, you can control the speed and the torque produced by the motor. So that's, I mean, the structure of the rotor, as we said. And that's the way that look in real life. Now we are going to explain how to produce the rotating magnetic field. And it's really a very interesting concept. And I remember when I was student, I was confused a little bit about this topic. So I understand the problem of it. So I will start from the basic concept. Because it's very important to produce magnetic field changing with time in induction machine. Except that you will not get mechanical energy output by rotating the shaft. Well, in front of you here, if you have a one winding, just to make it, it's like I have something like that. I tried to. So this orange, it's winding. There's a cylinder and there's winding. And this winding, the current coming like that in this ring and coming out from here. So if you look in the front of it, we'll do that. We'll use cross when the current is in, and the winding is behind this cylinder and then coming out from the other side, called A dash. So the in is A and out A dash. That's phase A. So I'm trying to show you, I mean, there's one phase here. I'm showing the current is in this direction, but that's what I meant, you know. And accordingly, the flux will be perpendicular to the winding, right? The flux will be coming out from here. You agree with that, or if you don't, I can explain. Let me explain it more detail a little bit. If you have one wire, one conductor, and the current going in this direction, so what you get? Magnetic field around. What is the direction of magnetic field? It would be like that. If you have different, you have like circles like that. That's not good color. You have circle in this direction. That's magnetic field, right? If you have another conductor, and this conductor, the electric current, the same magnitude, but in another conductor in the other direction. So what you will have? You will have magnetic field in this direction. If you are connected, if you connect both, you made a one wide, right? One turn. So the current going here, going this, in this way. So when you look at it now, it's one direction. The current going from this conductor continue its path till you get out in the other direction. So what you have magnetic field going, both they are like helping each other to go in like this, in this direction. So you can say it's going in this direction and going out. So if you make a little plane here, so you can say if you make pluses like that, means that the magnetic field going in and coming out the other direction, right? So we'll have many terms. So that's what I want to first with the basic one to understand how it's going to produce, because you have winding in the stator. All right. So that's, I mean, current in, that's current in, current out. And so the magnetic field will be like that. Since the magnetic field in this direction, usually when you see even in textbook having this, any textbook, the one in your hand, other one, you'll find they are making something and they call it AS axis. It means that the axis for the magnetic flux where the maximum or peak value will be aligned with. Okay, so if you have another winding, okay, let me just test you if you understand. If you have some stator like that and you have winding in this direction, call it for example B dash, so that's B, and that's B dash. So where is the peak of the magnetic flux or the axis? How you get it? You make a line connecting these two conductors, and then you make perpendicular on it. This is the BS axis. That's where the maximum, if the current, because of the current going in B and coming out of B dash like that, so the magnetic flux will be perpendicular to the line connecting B to B dash, and will be in this direction. So that's concept I want you to understand. So this is the axis of B. It is something else. You have stator and you have rotor. So for stator and rotor, if you have, that's the rotor, and let's do the stator. Well, and let's say in the stator you have two winding here, A and A dash. So obviously this is the, if you want to make the axis, you see this is the line connecting the conductor. So the one, if you make one perpendicular in it, that's the axis where. But how you sketch the flux? Well, it's simple. You can say that the flux will be, there's one around here, if you can. We make the stator even more realistic. The stator has like, yeah. So this one is the stator. And this is the red one inside the rotor. And what's between them? Air gap. Very important. We did in electromechanical conversion, energy conversion, we found out that the air gap is really important. The reluctance is bigger value, and that we focus on that. That's very important. So if you have magnetic flux passing, it will be like that. For example, going in this direction. Right. There is also another one here. That's magnetic flux. So the magnetic flux, there are two in the air gap. Focus on the air gap. There is one crossing from the stator to the rotor, and one crossing from the rotor to the stator. Yeah, flux. It's the same one. I know. But if you want to talk about the flux here, it's the same magnitude because it's the same line. But the sign should be different. So we have to agree about the sign convention here. So we'll say that if it's crossing from the rotor to the stator, we'll consider it positive. And if it's crossing from the stator to the rotor, we'll consider it negative. Okay? Because I mean, if you have like sheet like that, like I just showed you now, and there's flux. So if you talk about the flux in the front of it, that will be positive. It's out of it. And this one in, consider negative if you want to consider direction. So this one will consider negative, give it negative sign, and this will negative positive sign. All right. Now we are trying to build the basic that to understand how we'll do. Now, okay. So now I understand when I do this sketch for you, you know that's it's a conductor, and this is coming in, coming out, but the rest of the turn is just behind this cylinder of the stitch. And that will be AC axis, and that's if you have only DC current or constant current. Constant current in A and coming out of A dash. So you are going to have magnetic or MMF in at 0 angle and at pi. What does it mean? Because in this is the its axis. We said that the peak, the flux peak, will be along this axis, right? So it will be along this axis. This is, I mean, the axis. You can say if you want to assign angle. So we'll say this axis at angle 0. And if you move by angle, so this is will be angle pi over 2. This is pi, 3 pi over 2, and you go back to pi. All right. So actually, the magnetic field will be maximum along ES axis, which we consider it at 0, theta 0, right? If you don't move, it's at theta 0. So I make a line like that. And I make it positive. Why? Because the flux crossing from the rotor to the stitch. If you move to pi over 2, there is nothing, right? If you move to pi, yes, there is flux, but crossing from the stator to the rotor. And we agree we have to get it signed. So we distinguish between which one crossing from rotor to stator, which one crossing from stator to rotor. So I make the same magnitude, but in the negative sign at pi. And when you go 3 pi over 2, there is nothing. That 3 pi over 2, it's 0, no magnetic flux. And you go back again, if you go back again to pi, if you go to pi, so you should have another line here. It's you get back again. Well, because magnetic flux is going from one direction, our direction, and if it's a DC, so or one value, so that's where you're going to find. Okay. I'm trying to make it the maximum. But of course, if you tell me, I mean, do you mean that it is 0 here? No, there are, but less magnitude. But I don't do comprehend. So I mean, what is the maximum? If you are going to add more conductors and distribute them, so let's say I put 3 conductors and then 2 on the side and 1 on the side, like I'm making now distribution in a way. There are more conductor concentrated in the middle here, in the top and the bottom. Make like 3 turns. And then I make 2 turns, 1 turn. You got to remember that I'm talking about MMF. And MMF that will produce the flux, if you remember. MMF, it's equal N times I. The number of turns times the current. Why it's important? Because if you remember, MMF is responsible for producing the flux. And we said that it equal the flux times the reluctance. If you remember, we represented MMF as a voltage and flux as a current and the reluctance as a resistor. Okay, just in a way you remember it. So when you look for the one in the middle, you got 3 conductors on the top, 3 conductors on the bottom, you got 3 times I. If you have current equal, let's say 10 amp, so you got 10 amp in each turn, so you got like, and you have 3 turns, you got 3 times 10, you got 30. So you got MMF equivalent to 30 ampere turns, which will produce more flux. So it will be, I wrote it here 3. What does it mean? That's the maximum flux produced by the 3 conductors. The one that has 2, like on the side here, if you connect the line and you make it find that that's the 2. This is 2. It will produce flux, but shifted, right? Because it's a little bit shift from them in the middle. And also you have another 2 here, right? You got to the right and left. So, but the magnitude of the MMF less than. Why? Because you got only 2 conductors. So if you have 10 amp, you have 20. The other one was 30. So this is 20. So if you sketch, it will be here. If you move by theta, you'll find you got less. The height, I made it here like less. The biggest one, 3 times. The second, 2 times only, like 20. And then when you move further, you have only one conductor, 10 M. So your MF will be only 10. So it will be less and shifted. So every time you are moving away from the main axis, if you make the distribution this way, so you'll find that the magnetic field is getting less, less, less. So this is the way you're going to have it, by this distribution of the conductor. In AC induction machine, I'm sorry I made long to understand, because when I was student, they jumped to something magnetic field, I was confused. I didn't. So I did it like that till I get it. Then they have sinusoidally distributed conductors. Like the conductors in the machine, for every single phase, they distribute sinusoidally. Like the peak will be here in the middle and then decreasing in a sinusoidal way. If you look at the sine, for example, or cosine, whatever, if you go in the middle, that's like corresponding to sine pi over 2, that's 1. If you go a little bit less, it will be less than 1, and so on, till you get 0. So this is the way. And the top and the bottom, of course, because this is the in and this is the out. So now we can find that the magnetic field, it looked like cosine wave. Because I mean, the axis, here is the maximum, right? This is the axis. AS axis. That's by the way, that's only AS. I'm making only one phase a time, so you understand. So this is the axis AS. What is the maximum? And every time you are moving, you will be, the magnetic field will be less, 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 and then when it flip, when you come here, it will be going in the other direction. So that's, I mean, the field, or MMF, if you wish, I like to call it MMF, or sometimes I call it just F. The magnetomotive force, that's the way that will be done for one phase. By the way, I didn't yet change the current. I'm considering DC. Because you look at it, you say, oh, we have AC current. No, I have DC till now. Why it's changing? That's the position that you have to pay attention. This is the position. What's theta? That's theta. We agree from that. When theta equals 0, you got the maximum. Don't be confused, because you look here in the top and the bottom maximum, and then I'm making the maximum at the 0. Yes, because it's perpendicular. The magnetic flux is perpendicular. We agree about, if you have conductor like that, then that's the magnetic field perpendicular on it. Far by pi over 2. So this is far from this pi over 2. That's right. But this is not with time. That's with position. That's theta. I have DC. I didn't get AC. That was confusing me a lot, but I got it in the end. It takes time, but now I'm going to apply AC. When you apply AC, this one changing position, you find they have different magnitudes according to the current. Because when the current changes the AC, you got to understand that that's, I mean, now the current at T1, which is equal 0, it was the max. So what you get, that's T1, the max. And when you go to T2, the current is less. So what will happen? The magnetic or the magnetomotive force, F, will be less. But it's the same. In the same graph, you just make another one with time. So that's horizontal with the position, and then the magnitude changing, up and down according to the time. So if I ask you, what about the magnetomotive force when it reaches pi over 2? I'll tell you it will be 0, because that will be 0 M. But at T1, it's the maximum. So this is the curve, the maximum. And it changes with the position in the same way. When you go for T2, the current is less, that's D2. Okay, this is the axis, by the way. That's where the maximum you can see. When you go for T3, you are on the other, it changes direction. What does it mean it changes direction? It means that here, instead of the current here going in this direction, no. The current will be going here, coming out here. Going in A dash, coming out of A. So the flux will change the other direction. That's why you can see there that it's changing. And already we did that here in this graph. So what I'm saying that that's at T3. It's the same but flipped and T4. So in x-axis, the magnitude is changing with the position. The peak varies according to the time. This is only one phase. All right. If you don't understand, you have to ask. So one phase. Now, I want to apply three phase. Yes, go ahead.
All right, so on the left side, like the left graph,
Yes.
it makes it look like we're taking time increments at different moments.
Yes, exactly.
But on the right graph, it looks like we're taking one time increment.
No, I mean this curve for example, corresponding to the value of the current at T1. But it's changing with the position. I'm telling you the magnitude where is with theta equals 0, 10 degrees, 30 degrees along the horizontal. But the peak, you see, I mean, let me just make this big mass. If you look for here, T1, that's the value of the current, 2n. So we do at T1 this curve. That's the magnetomotive force at T1. At T1. Then when I move to T2, the value of the current is equal 1 amp. So the peak will be reduced to the half, because magnetomotive force equal n times I. N, of course, fixed. I now change, becomes from 2 to 1. So now I have the magnitude. So if this is, for example, if this is 20, so I go at 10, that will be the maximum. And then I'll make the other, let me choose another color. Okay. So that's T2. That's the magnetomotive force at the instant T2. And if you go to T3, that's T3, it's equal to -1. So we'll have like T2, but flipped. You see, it's the same T, that's T3, flipped, negative. If you go for T4, it's the same as T1, but flipped. So we go again. Look at the, focus on the peak of each curve. The peak of each curve of magnetomotive force is proportional to the current at specific instant of time. So if you wish, say what if you want to cover the whole area, you can say that you shade all this, you shade all this, you shade all this. That will be the change will be covering, you know, this. If you because you are going to fill it by every single second, then you'll find that the magnetomotive force taking the shape, the change with the position for one phase. When you have AC. So what happened if it's DC? You will have only one curve. If you have DC, one curve. If you have AC, you have this curve flipped and the space between them filled. You have all possibilities from positive to negative. That's one phase. If you go now for a three phase, that's three phase. Very interesting. Every one of this single phase have the same magnetomotive force belongs to it. But every one will be shifted by 120. I'm not talking about time. I'm talking about position. Because if you look at A, that's A and A dash. So that's the axis, AS. And if you look at B, that's B and that's B dash. So if you connect B, all right, and you have to make the right direction, it's going B and B dash, so B in this. So that will be the axis. So, that's the axis of B. If in the right position, B and B. And see the same thing, you can draw the line, make perpendicular. So now each one has its own magnetomotive force in a special direction, but they are spaced by 120 degrees, not in time, in position. Because when you locate it BB dash, you intentionally, we do it, we intentionally will make a space by 120 degrees, each phase from up, from the other one, 120 degrees, mechanical degrees. What this will affect? That's very interesting, very smart idea. Now you have a three phase, that's IA, IB, IC. Take a T node, for example. T node. What is the value? That's IA, by the way. You got to know this is IA. So IA has the max, right? What's IB? What's IC? By the way, this is a third degree. So if you can calculate, you can find the value for this value and this value. Look at T node. So what is the value of IA? What is the value of IB? What is the value of IC? IA is equal the peak, I max. Why I'm saying max? Because for sine wave or cosine wave, if you say cosine wave, so you say IA equal I max cosine omega t. What about IB in three phase? I max cosine omega t minus 120. What's IC? It's equal I max cosine omega t plus 120. So if you go at this position where t is equal 0, when t equals 0, you substitute. So Im cosine 0 is equal 1, so Im. What about IB? Will be cosine negative 120. So to be like negative, I think this will be, that's right. What's cosine 120? That's 60. No, 1/2 will be 1/2, right? Check, but negative. Negative 1/2. Im and IC negative 1/2 Im. Let's take this position. IA in the same direction, positive. By the way, is like treat as DC. You say at t equals 0, you got this value and this value, treat as DC. So what happened here? So it will be in the same direction of this axis AS, right? So you have magnetomotive force proportion to the Im. Proportion to Im. Okay, so let's say that FA equal, of course, be equal NIM, right? NIM. Call it F max. Call F max NIM. IM when IM multiplied by N, F max. So you have F max. What about B? B is negative. What does mean B is negative? It means the current will be in the opposite direction. I'm making this red arrow when it's positive. So I'm not going to have it in this direction. I'm going to have it in the opposite direction because I changed the current. The current instead of going from B, coming out of B dash, coming from B dash, coming out of B. So it will be flipped. So it will be in this direction. That's DS. That's where is the F. What is the angle between this one and this one? That's equal half FM. Why I'm saying equal half FM? Because the current IB is equal minus 1/2 IM. Now I took care of the negative, but I mean 1/2, it will affect the magnetic force by half. So we have FM. What about C? C, the current negative, so it will be go in C dash, that's C dash, and coming out from here. So if I make line like that, it will be coming in this C dash, come out, so it will be like that, perpendicular. That's C. So it will be in other direction. I'm just interested to know that's also half FM. So what is the angle? The angle between because this angle they are equal is 30 or 60. Can you tell? Well, if this is 120, if this is one, that's I mean. So it will be, if you have it, this one, and originally you have it here, that's 120, and now I flip it. So 120 would be 60, right? So that's 60, that's 60. So what is the resultant? The resultant will be Fm plus 1/2 Fm cosine 60, 1/2 Fm cosine 60, so plus Fm cosine 60, right? Because you have 1/2 and 1/2, make it to Fm cosine 60, and cosine 60 is equal to 1/2, right? So you have Fm plus 1/2 Fm, you got 3/2 Fm in this direction. So now you have resultant magnitude of force flux horizontal in this direction, and the magnitude is equal to 1.5 maximum. Was mean 1.5 NIM. Call it maximum, 1.5 F max. Let's take one time, see what's happening to magnetic field. Take now T1. T1. At T1, what is the value of IA? 0. That's good. Let me just erase the things now. We have new time. So you have IA equals 0. And what about IB? IB has this value. This value, it's obviously equal to radical 3/2 F max. Because this is, I mean, from this one, it's equal to pi over pi, that's right. So you put 180 in IB, 180 minus 120 will be 60, will be, so that radical 3/2 is not half like this one. What about IC? On the same, and you see what I'm looking at the same time instant T1. At T1, IC will be equal negative this value. All right. So IA is equal 0. IB equal radical 3/2, and the other one negative will be negative. Okay. I'll go back to my mass sketch here. So I don't have AS. Nothing here. It's 0. I'm going a new one. When you do, I want IB. IB is positive. Okay. IB is positive, be in this direction, the normal one. So if I make, just allow me to, I can do it right. That's the magnitude is equal radical 3/2. And we said 120, 19 plus 30, you make 120, right? That's the B. The C, negative. Okay. I got to know what the C, original C. The C, that's C dash, that's C, and C negative, it means I'm still going at C dash, coming out would be the same, CS. So to be like that. Radical 3/2 FM 30. AS is 0. So now look at the resultant. The result will be up. You can make resolution, so you get radical 3/2 times cosine 30 times 2. So it will be 2, cancel 2, you get radical 3. And cosine 30 is equal radical 3/2. 3/2. Again, you got 1.5 F max. So what does it mean? It means the magnetomotive force is, the magnitude is equal to 1.5 Fm all the time, but it's rotating in this direction. And if you do, I'm not going to waste the time. If you do T2, it will be like this. We produce something called rotating magnetic field. The magnitude of the rotating magnetic field is fixed, but it's rotating in the direction of the anti-clockwise direction. And even they found the speed of the rotation. You can do the speed of it. But that's the important part. That's how they created what they call rotating magnetic field. And by the way, rotating magnetic field is a very essential concept in any AC machine because they don't rely on producing current. So that's very important to understand. That would be equal 1.5 maximum The magnet also like that, but it's rotating in this direction. Or if you want to change the direction of the rotating magnetic field, it's very easy. Exchange phase B and C. Put B, winding of B instead of C, and that's it. You will get the other way to rotate around. Okay. I hope that you got to understand. Of course, there is, I mean, that's a graphical method for proving the rotating magnetic field. There is algebraic one, but I agree with the graphical make more understanding.
Real quick.
Yes.
Test 3 on Friday, is it going